energy changes for GCSE, iGCSE and general chemistry. Getting the best from chemistry explained requires you to participate by writing notes, completing tasks on paper or on tablet. Go through the lessons at the pace which suits you. Go back to previous slides or skip forward if you feel confident. Most importantly, when prompted, pause the lesson, complete the task, take your time, think it through. Only restart the lesson when you're ready to correct your work. The overview will be exothermic and endothermic reactions. We'll look at reaction profiles and activation energy. For those doing iGCSE, I'll run through some terminology, enthalpy change and delta H, experimental methods, and then calculations involving bond energies. Exothermic and endothermic reactions. A very important idea we will borrow from physics. Total energy is conserved in chemical reactions. We do not create or destroy energy. The total amount of energy is conserved, kept the same. However, thermal energy may be transferred from the reaction to the surroundings. So chemical reaction takes place, energy is transferred, thermal energy is transferred to the surroundings. Therefore, the thermal energy in the surroundings increases and the temperature increases. We call that type of reaction exothermic. So we need to explain the temperature rise. Chemical energy in the reactants is moved to a different energy store, thermal energy, in the surroundings. Overall energy is conserved, but chemical energy is moved to thermal energy. Hence, there is a temperature rise for an exothermic change. What does that look like in an energy level diagram? Well, here's energy, course of the reaction. The chemical energy of the products is less than the chemical energy of the reactants. What's happened to the energy? It's been transferred to a thermal energy store of the surroundings, and the temperature of the surroundings goes up. However, it's also true in some reactions that energy is transferred from the surroundings to the chemical reaction. That means the thermal energy in the surroundings decreases and the temperature of the surroundings decreases. We call those types of reactions endothermic. Now, for an endothermic change, the temperature drop is again explained by a change in energy store. Thermal energy in the surroundings is transferred to the chemical energy store in the products. So, although energy is conserved, the chemical energy in the products is higher than in the reactants. Pause. Can you produce an energy level diagram to describe that, as I did on the previous slide for exothermic? Pause, come back when you are ready. Okay, so here's my energy diagram. The products have more chemical energy than the reactants. That's always going to be true for an endothermic change, a change that causes a decrease in temperature of the surroundings. The chemical energy of the products is more than that of the reactants. So I'm going to give you a few problems on the definitions of exo and endothermic. Here are 4 statements. Can you assign the correct energy transfer and temperature change of the surrounding to exothermic and endothermic? Each of these 4 statements fits somewhere into that table. Pause, come back when you have your answers. Okay, so in an endothermic reaction, energy is transferred to the chemical reaction, and therefore there's a decrease in the surroundings temperature. For an exothermic reaction, of course, there is an increase in the temperature of the surroundings, and that's because energy is transferred to the surroundings. Then a simple but clarifying task. Identify the correct reaction type. Mixing citric acid and sodium hydrocarbonate, decrease in temperature. Neutralization, increase. Which is exo and which is endo? Pause, come back when you're ready. Okay. Mixing citric acid with sodium hydrocarbonate is an endothermic change. In AQA specifications, for example, are expected to recall that particular reaction and reaction type. Of course, neutralizations, therefore, are exothermic. In most specifications or courses, you are expected to know that neutralizations are exothermic. So here are a collection of types of reaction or uses involving exo and endothermic reactions. Pause and assign each reaction type or use to the correct classification. Pause, come back when you're ready. Okay, so let's run through these. Combustions are exothermic, of course. Thermal decompositions are endothermic. Self-heating cans have an exothermic reaction within them. Sports injury pole packs again have an endothermic reaction as part of the pack. You may be expected to know that citric acid and sodium hydrogen carbonate are endothermic or react endothermically. Neutralizations are exothermic, and of course, hand warmers involve an exothermic change, as do oxidations. Now, you are expected to know those examples of endothermic and exothermic reactions. If you didn't, you might profit from repeating this particular slide a few times until you have got those in your memory. Reaction profile or pathway diagrams. Reaction profiles include the concept of activation energy. For example, an exothermic combustion of a fuel such as methane, which is the gas principally burnt in a Bunsen burner, will only occur when an initial input of energy is supplied. To achieve a burning Bunsen, of course, you need to ignite with a flame. This is an initial input of energy. For all reactions, there's a certain minimum energy needed so that the reaction can start. The name for that certain minimum energy is activation energy. Activation energy is added to an energy level diagram to create a reaction profile or reaction pathway diagram. So let's look at an exothermic change. The products have less energy than the reactants, but there's an energy barrier between the reactants and the products, which has to be overcome by an input of energy. That input of energy is the activation energy, which is the difference between the initial energy level of the reactants and the top of the activation energy curve. Pause, produce a similar chart for an endothermic change. Restart when you're ready. Okay, so if we look at an endothermic change, our products have more energy than the reactants. We need to go from the energy level of the reactants to the peak of the activation energy curve. So that will correspond to, of course, the activation energy. Notice that the activation energy usually is required to have a directional arrow because, of course, we are putting energy in, so the energy is increasing, so we need to just show that with an arrow with a direction. The overall energy change of reaction is also shown on a reaction profile. Let's look at an exothermic change. So here we have the products with less energy than the reactants. The overall energy change is going to be the difference between the energy level of the reactants and the energy level of the products. So marked in red, there is the overall energy change of reaction for an exothermic change. Pause and produce a similar diagram for, or profile for, an endothermic change. Okay, so to reveal the endothermic change, products more energy than reactants. Where is the overall energy change? Well, the overall energy increases, so we have an upwardly pointing arrow. Notice here we had a downwardly pointing arrow. The energy of the chemicals decreases. Chemical energy decreases, so we have an arrow pointing down. Here for an endothermic change, the chemical energy of the products is greater than the reactants, so it's increasing, so we have an upwardly pointing arrow to indicate the overall energy change of reaction. So here is a problem. Draw the reaction profile for the neutralization reaction between sodium hydroxide and hydrochloric acid. Indicate the activation energy and the overall energy change of reaction. Pause, produce that reaction profile, compare it to mine when you're ready. Okay, so here is my basic reaction profile. You should recall that neutralizations are exothermic. So the products have less energy than the reactants. The activation energy, of course, you would mark here. You might, if you've done rate of reaction, you know that activation energy is capital E small a. The overall energy change of reaction, like so. Notice the chemicals involved rather than reactants and products. We write the actual identities of the chemical species in the chemical reaction. Enthalpy change, delta H. So this particular slide applies to iGCSE only. There's some additional terminology Chemical energy is known as enthalpy, which has the symbol H. So rather than having energy on your reaction pathway diagrams, we would have enthalpy of system. The overall energy change, therefore, is a change in enthalpy, and we use the symbol delta to indicate change. So the overall energy change of reaction is an overall enthalpy change, delta H. Delta H is negative for exothermic reactions and therefore obviously is positive for endothermic reactions. There is a great deal of experimental work that can be done in this topic, energy changes, so let's look at some experimental methods. So let's work from a particular problem. A typical GCSE problem would be investigate how concentration change affects the temperature change of a neutralization. So our setup would be something like this. A volume of hydrochloric acid at 1 mole per decimeter cubed is added to 25 centimeters cubed of 1 mole per decimeter cubed sodium hydroxide, and the temperature change is measured. In this case, it rises by 6.2. So how would you change the independent variable to reach a conclusion? What would the dependent variable be? And what would you need to keep the same between the various trials? What would be the control variables? Pause, think this through, take your time, come up with some ideas. Okay, so the independent variable, let's say, is the concentration of acid. You would need a further minimum of 3 different concentrations. 0.75, 0.5, 0.25 would be perfectly acceptable. The dependent variable, of course, is the temperature change. But what would you need to keep the same? What would be the control variables between each trial? Well, the volume of acid would need to be kept the same. The volume of sodium hydroxide would be the same. And of course, the concentration of the sodium hydroxide would be the same. You're only changing one variable. The independent variable, in this case, the concentration of acid. Let's have a little bit more detail to the method. What measurements would need to be taken? What would be the most obvious causes of error? And what about choices of apparatus and instruments? So let's start with measurements. What measurements would you need to take? Pause. Come up with some ideas. Okay, so you would need the initial and maximum or minimum temperature of the reaction mixture. And obviously you also need to be measuring the volumes of solution. What would be the principal causes of error? Come up with a couple of ideas. Okay, to reveal mine, inaccurate measurement of volumes, and of course heat losses to the surroundings. So let's look at some apparatus and instrument choices. The thermometer, obviously we need. Don't forget to include that in your apparatus list. But which would be better, a measuring cylinder or a pipette for measuring 25 centimeters cubed? Well, the pipette, it's more accurate than the measuring cylinder. Then how could we reduce these heat losses to the surroundings? If we used a polystyrene cup rather than a beaker. Polystyrene is an insulator, so heat losses to the surroundings would be greatly reduced. Calculations involving bond energies. Calculations involving bond energies use the idea of a reaction occurring in two distinct steps. Firstly, the breaking of the bonds in the reactants. This absorbs energy, it is endothermic. And the second step is the making of bonds in the products. This releases energy, it is exothermic process. So two different processes, breaking of bonds in the reactants absorbs energy, making of bonds in the products releases energy. So if we look at a diagram here of an exothermic reaction, this process here to the peak of the activation energy curve, this is about breaking bonds. It's endothermic. The process here, that is exothermic, and that is making bonds. So exactly the same applies to an endothermic. No difference. This process is about breaking, and then the second process is about making. So breaking bonds is endothermic. We can see here there's a rise, an energy input, and an energy release in making the bonds. That is exactly the same situation for endothermic reactions. Now, every covalent bond has a bond energy value. This is the energy required to break 1 mole of the bond. Here are some examples. A carbon-hydrogen bond, 413 kilojoules per mole. Oxygen-hydrogen, 467. Hydrogen-hydrogen, 432. Oxygen-oxygen double bond, 495. Carbon-oxygen double bond, 745. As you would expect, the double bonds have a higher bond energy value. That is, they are stronger. So I'm going to model one problem. Calculate the overall energy change of the reaction between hydrogen and chlorine to make 2 moles of hydrogen chloride. Now the overall energy change is going to be the energy needed to break the bonds plus the energies released on making. The bonds broken, endothermic, is given a positive energy value. The bonds made are given a negative energy value. What bonds have got to be broken? Well, there's a hydrogen-hydrogen bond between the 2 hydrogen atoms in the hydrogen molecule. Similarly for the chlorine, there's a chlorine-chlorine bond. But these are molar numbers, so we've got 2 hydrogen chlorides. So we've got 2 hydrogen-chlorine bonds to make. From a data source, we've got 432 for the hydrogen, 242 for chlorine. Hydrogen chlorine is 427, but we multiply that by 2 and we give it a negative sign. Bonds made are given a negative value, so bonds broken are given a positive value. So the positive values minus the bonds made values. Add that all together, comes to minus 180 kilojoules per mole, and that fits with the reaction being exothermic. More energy is released. These values, the energy released on making the bonds, is greater than the energy absorbed on breaking the bonds. So that's an explanation for this exothermic value. We know it's exothermic because it has a negative value. So the reaction is exothermic, more energy is released, making the new bonds than is absorbed in breaking the existing. This value, 2 times 427, is greater than 432 plus 242, comes to minus 180. That is, more energy is released by making than is absorbed in breaking. So there are a couple of problems. The first one is on this slide. Calculate the overall energy change, or if you're doing iGCSE, the enthalpy change delta H for this reaction, hydrogen and oxygen forming 2 moles of water. You'll need some bond energies, which are here to the right. Pause, solve the problem. What is the overall energy change? Come back when you have completed that task. Okay, so the first thing to do is to identify the bonds that need to be broken. Well, we've got hydrogen, hydrogen twice, and oxygen, oxygen double bond. Don't forget, oxygen forms O2 with a double covalent bond between the oxygen atoms. Water, oxygen, hydrogen twice in each water molecule, but there are 2 water molecules. So if we look at the bonds that are broken, it's 2 times the hydrogen, hydrogen, and 1 times the oxygen, double oxygen. We get the numbers from the table. Hydrogen, hydrogen is 432, but times 2 comes to 864. There's 1 oxygen, oxygen double, which is 495, comes to plus 1359. Now we need the bonds that are made. Well, we've got oxygen, hydrogen twice in a water molecule, but there are 2 water molecules. So 4 times the oxygen, hydrogen, 4 times 467 comes to 1868. But we need to give making bonds a negative sign. We then add these 2 numbers together. So the overall change is plus 1359 minus 1868 comes to minus 509. This is exothermic. The energy released on making the bonds is greater than the energy absorbed to break. Gives an overall energy change with a negative value, which is typical of exothermic reactions. So here is a second problem. Calculate the overall energy change, or delta H, the enthalpy change, for methane's combustion in oxygen. Of course, you will need some bond energy values. Here is a table with the relevant values. Pause the lesson, complete the calculation, come back to check against my solution. Okay, so the first thing to do is to identify the bonds broken and made. So carbon, hydrogen 4 times, oxygen, oxygen double twice. Carbon dioxide is carbon double bond oxygen, carbon double bond oxygen. Water, oxygen, hydrogen, but there's 2 moles of it, of course. So the bond's broken, 4 times the carbon, hydrogen, 1652, 2 times the oxygen, oxygen double, comes to 990. Totals plus 2642. Bonds broken are given a positive sign. The bonds made, we've got carbon double bond oxygen twice and oxygen hydrogen 4 times. Totals to 3,358 and is given a negative sign. Bonds made are given a negative energy value. The overall is achieved by adding them together, comes to minus 716. The negative sign indicates it's exothermic, which the explanation is the energy required to break the bonds is less than the energy released on making the bonds. Of course, in an endothermic reaction, the opposite argument holds. Now try some problems from your textbook or an online source for which you have access to answers. Maths and Physics Tutor is a good online resource of course, there are others. Complete a number of problems until you are consistently correct, and then move on to the next lesson. I hope you've learned some chemistry, and I'll be grateful for any feedback via a YouTube comment, and of course, please like and subscribe.